Assalamu alaikum. In this lab, we would be implementing an AVL tree. An AVL tree is a height balanced tree, as we have already discussed in the sessions. It is a binary search tree, but it is a self-balancing binary search tree, which means that the height of this tree always remains log of n, where n is the number of nodes. So for example, if you have 64 nodes, so maximum height of this AVL tree, the maximum height of a normal BST tree, binary search tree, which is not an AVL tree, can, in worst scenario, can go up to 64 if at every level there is only one node, and then the next node is on the next level, and the next node is on the next level. So in this way, if there are 64 nodes, the worst case scenario can be that every node exists on a separate level, so it would give us a height of this tree 64. So now in this case, the disadvantage is that basically that you cannot take the advantage of BST. The advantage of BST was the advantage of the BST array when binary search is applied on this ordered array. The searching is performed in log of n time, whereas if a tree is not height balanced, so this does not give you the opportunity to use it as binary search on ordered array, and the searching time and insertion time both would become n instead of log of n. So to avoid this scenario, usually binary search trees are implemented as AVL trees. AVL is named after the inventor of this data structure. So in this case, we would be in this lab we would be implementing an AVL tree. For example, in this example, this example shows AVL tree, an AVL tree on the left column, in the left column, and not AVL or non-AVL tree in the right column. So both are binary search trees because they meet the property which is stated here. For example, keys of left subtree is less than key of root, which is less than key of right subtree. So this is the basic property that validates a binary search tree. So both these trees are validating this property, but still one is AVL tree and the other is the right side is not an AVL tree, because an AVL tree, each of the node in an AVL tree validates the property that the balance factor of each node is has a maximum difference of 1. So if we analyze the tree on the left side, in the left column, we see that 4 has a balance factor of 0, 5 has a balance factor of 1, 6 has a balance factor of 1, 12 has a balance factor of 1, similarly 18 has a balance factor of 1, 11 has a balance factor of 0. So all the nodes validate the AVL property. But if we analyze the tree on the right side, 2 has a balance factor of 0, 4 has a balance factor of 1, 5 has a balance factor of 1, 8 has a balance factor of 1, 2, 3 minus 1, 2. So 8, the AVL property is violated at the node 8. Okay, so and if you analyze it further, let's suppose that 2 was the last insertion. Okay, so in that case, basically before the insertion of 2, the AVL property at 8 was validated. For example, 8 before the insertion of 2, 8 had a balance factor of 2 minus 1, 1. So it was an AVL tree. But as soon as we inserted 2, the balance factor at 8 became unbalanced. So insertion in an AVL tree is basically the same as the binary search tree, but we have to validate that every node is maintaining the AVL property. So it has a few differences from the BST, normal BST insertion. So insertion is we must augment or modify the standard BST insert operation to perform some rebalancing if needed. Okay, so when a rebalancing is needed, there are two kinds of rebalancing schemes which are called rotations in the in AVL tree concept. So we would be the left rotation and right rotation fixes the imbalance at a node. Okay, for example, in this case, if we consider T1, T2 and T3 are the subtrees of the tree rooted with Y, so Y is the root node in the left subtree and X is the root node in the right column tree. Okay, so if this Y, if we perform a right rotation, it's basically a rotation between Y and X, which makes the tree that Y becomes the right child of X becomes the root, and T1 becomes the right child of T1 becomes the left child of X, T2 and T3 become the right and left child of T1. Okay, so it's basically the tree has been rotated towards right, and the rotation was between X and Y. So when when Y becomes the right of when Y becomes the right of X, we have to update the connections and links between them. So if you see, in case of both trees, they still validate the BST property, because the BST property for the right side tree is that T1 should be less than X, which should be less than T2, and this T2 should be less than Y, which should be less than T3. And in case of right rotation, still T1 is less than X, which is less than Y, or you can say T2 is less than T1, which is less than T3, which is less than X, which is less than Y. So the BST property is validated in both the trees. Okay, so the steps which are needed to be done for inserting a node into AVL trees are that we perform a standard BST insertion. Let's suppose the node is W. So to insert this W, we perform standard BST insertion, like comparing this value of the key value of this W node with the root node, and if it is less, then come to the left subtree of the root node and keep on going to left if the value of this W remains less than the value of the nodes, and move towards the right subtree if the value is greater than the value of any node. Okay, so then once this W node is inserted into the tree, we start traveling up and find the first unbalanced node. For example, if W is inserted assume that the W is inserted at in place of T1 here. Okay, so if this is the insertion of W, then we start traveling to X and to Y and to Z. We start moving towards root of the tree, starting from this newly inserted W node, and we find the first node that became unbalanced because of the insertion of this T1. And if you think a bit, then only that node would be the chances of an unbalance on a node are only there for a node whose height has been changed. Okay, for example, if assume that there was no T2, okay, and you inserted T1 beside beneath X, okay, so under X, so in that case the height of the X has been incremented. Okay, x had a height of 0 initially before the insertion of t1, but after insertion of t1 x has height 1, and because the because the height of x has been incremented, because of that the height of y has also been incremented, and the height of z has also been incremented. So every node, insertion of a new node increments the height of its ancestor nodes. Okay, and so we find out the first node on the route from the newly inserted node towards the root, which became unbalanced. Okay, and we perform the rotations over there. So once that node is found which has been unbalanced because of the new insertion, there can be 4 possible cases that needs to be handled, as x, y, z can be arranged in 4 waves. Okay, we assume that w is the node which has been inserted, and z is the first unbalanced node, y is the child of z, and x is the grandchild of z. For example, here if t1 is to be considered as w, then z is the node where the imbalance has occurred. For example, if you assume that there is no t2, okay, we just let's suppose there is only w. Okay, now if you compare, x had earlier a height or a balance factor of 0, now it has a balance factor of 1, so it is not violated. Y has a balance factor before insertion of w, it has a balance factor of 0, but now it has a balance factor of 2 minus 1, 1, so it's still not violated. Z, before insertion it had balance factor of 2 minus 1, 1, it was not violated, but now after insertion z has a balance factor of 2, because 3 minus 1 is 2. So z is the first unbalanced node on the route from w to z. Okay, so we assume that z is the first unbalanced node, y is the child of z, and x is the grandchild of z, which is the case here. Okay, so in this case 4 arrangements can be there are 4 cases basically which can give birth to this unbalance. The first is y is left child of z and x is left child of y. For example, y is left child of z and x is left child of y, and then w is inserted. We are not concerned with that w is inserted on left or right, because we are considering the from the parent of w towards the root. Okay, so first case is z is that y is the left child of z and x is left child of y, which we call left case, because the insertion which caused this unbalance was rooted towards the left child of the unbalanced node. Okay, x is the left child of y, y is the left child of z, and z is unbalanced, so it's a left case. Then the second case is y is left child of z and x is right child of y. Okay, for example, it can be a case for example, here it was the case like this, let's suppose, and then this w was inserted as the left child of x. Alright, so now this is the case where y is the left child of z but x is the right child of y. So the new insertion under x is caused by a left right insertion. So this is left right case. Similarly, y is right child of z and x is right child of y. This is right case. And y is right child of z and x is left child of y. This is right left case. We have discussed these cases in the sessions as well. So these cases are handled with there are cases, for example, left case and right case. These both cases are handled by only one rotation in the opposite direction. In case of left case, you perform right rotation. In case of right case, you perform left rotation. But left right case and right left case, these both cases are handled by two rotations. In case of left right case, you perform first rotation towards left and the second towards right. In case of right left case, you perform first rotation towards right and other rotation towards left. So